focus of this unit of work is digital media. In order to have a clear understanding of this topic, let's have a look at the meaning of these two words. The word digital comes from the word digit. A quick look at the dictionary shows us that the word digit can have a couple of common meanings. The first is digits as in mathematics, the numerals 0 to 9 that are used to make up our numbers. But the word digit also refers to fingers and thumbs. This is no coincidence that the same word refers to these two things, but more on this later. Now the word media. In common everyday language, we refer to the media, our means of mass communication. Traditionally, these things such as radio, television, newspapers and magazines. The word media is actually the plural form of the word medium. The word medium refers to the means by which something is communicated, the way that the message is carried. So as we commence our study of digital media, let's keep in mind the meanings of those words, digital referring to numbers and media being the ways in which we communicate. As mentioned earlier, there is a relationship between numbers and our fingers and thumbs. Our fingers and thumbs were really our first counting device, an aid to counting. It is no coincidence that we count in lots of tens, the total number of fingers and thumbs we possess. Some people would have us believe that counting in lots of 10 is somehow easier than counting in other groups, that somehow it is magical. But it is not. It's just that we use it all the time. Perhaps if the cartoon world of The Simpsons was in fact the real world, we would be using a counting system based on 8, and we would find this easier than counting in groups of 10. Look at this number. Quickly, what number is it? If you answered 346,182, you worked that out pretty quickly. Well done. But there is in fact quite a lot of complex mathematics behind what you just did. Complex mathematics, I hear you say? Well, yes. Because what you in fact did was this mathematical equation. And you did it far more quickly than this accelerated video. How is this possible? Is this some kind of magic that proves that counting in lots of 10 is easy? No, this is not the case. It's just that you've been doing this most of your life. If we had a really big number, we would find this harder to put into words because we don't use those very large numbers all the time. Our counting system is based on 10 digits. In the previous example, we were looking at 3 lots of 100,000 plus 4 lots of 10,000, etc. Another way of expressing these numbers is as powers. So 100,000 is 10 to the power of 5, 10,000 is 10 to the power of 4, 1,000, 10 to the power of 3, hundreds, etc., etc. As we move to each new column to the left, the power of 10 increases by 1. Just a reminder, any number to the power of 0 is 1. Similarly, any number to the power of 1 is itself. It doesn't matter what the number is. Because we are so familiar with these numbers, we don't have to apply the mathematics. We almost instantaneously recognize the numbers. It's not that this group of 10 digits are somehow special. We just use them all the time. We describe our counting system as base 10. That is, all based around 10 digits, from 0 to 9. This is also known as decimal counting. Once we use up the 10 digits, we start to combine them to make more complex numbers, adding new columns that have values increasing by lots of 10. A computer does not have fingers to help keep count. It is powered by electricity that either can be on or off. 2 possibilities. Computers use a counting system based on 2 digits. It only uses 2 digits and is called binary counting. Those 2 digits are 0 and 1. Once we get past 1, we combine the digits together to form more complex numbers, following the same rules we used for decimal counting. The digits 0 to 1 are called binary digits, and when we combine those words, we get the word bit. One bit of data is simply a 1 or a 0. When we put together 8 bits of data, this forms 1 byte. So 8 bits, 1 byte. The binary counting system works in exactly the same way as our regular decimal counting system. That is, we are going to end up with a series of columns, except our base is 2. 2 to the power of 0, 1, 2, 3, 4, 5, 6, 7, etc. So here we can see 8 bits of data represented. Each of the columns working from right to left have a value of 1, then 2, 4, 8, 16, 32, 64, and 128. Each column doubles the previous column. So as we begin to count, we start in the first column with 0, then 1. But now we've used all the digits in this counting system, so we must move to the next column, which has a value of 2. So 1, 0 means one lot of 2 and no lots of 1. 3 is one lot of 2, one lot of 1. Now both columns are full, so we move to the next column, which is 4. This movement from column to column is exactly the same as what happens in our base 10 counting system that we use every day. Here we see a counter moving from 0 to 255, base 10, also being counted in base 2 using 8 bits of data. So to summarize, using 8 bits of data, or 1 byte, we can represent any whole number from 0 to 255. That gives us a total of 256 unique combinations. Okay then, so now it's your turn. What base 10 number is represented by the base 2 number shown here? So we have one lot of 64 plus one lot of 8 plus one lot of 2 plus one lot of 1. When we add these numbers together, we get 75. So let's try another example. What is 10101010 as a decimal number? This represents one lot of 128 plus one lot of 32 plus one lot of 8 plus one lot of 2, which gives us a grand total of 170. One final example. And guys, this is a clue to the title of our unit of work. This is simply one lot of 32. So, do numbers really say...
What's going on?